Yeah, I guess, kind of. Well, so what I want to do is take the webcam and I don't know where I want to put it. I guess like on Gus's head, because then when he looks at stuff.
GoPro.
Yeah, there you go. Yeah, so I can put it somewhere. Anyway, so that's going to be the new format. I'm not doing it today because it's only worked once, and I want to debug it a couple more times and figure out where to put this camera. I would look goofy when I walk around.
Do it in CS440.
So
Yeah, I
I
do.
do a question.
Yeah, well,
When are you gonna get that projector working and have cat videos play on that projector in class?
Yeah,
Well, I
right?
have to find a new video card for this computer before I can do that. And because it's got two DVI outputs, and these projectors, I mean, don't have like HDMI or DisplayPort or DVI or anything else modern. It's got VGA. It's got the composite plug that your VCR has on the back of it. It's got S-Video and it's got component. All analog.
I have an HDMI to VGA converter that I can donate to the cause.
I don't have an HDMI port on this.
Oh, that's too bad.
So yeah, I mean we're stuck on that video card, but all the Intel machines around here have the right card, and there's a machine sitting over there in the server room that nobody uses. It has the right card, and so I just got to take this computer and take it apart and replace the video card and put it back together, and we'll be set, or else replace it entirely. Oh yeah, so I was going to talk about something today. Like we're in class, aren't we? So I should be teaching.
There's
Okay.
like 2 people.
Yeah, I know. We're like way down on attendance.
Oh, Tiger's right there.
Yeah, he's over there. Yeah, he's working on this course, so that's fine. So I want to talk about processes a little bit more today, and I thought that we'd go ahead and do create some zombies and observe them, and then we can eventually dispense of them by waiting on them. And so we'll do some study of how the process model works on here. And then I'd like to make a demo where we have a process, and we'll make a child process, and then we'll use the child process to execute things. We'll set up a bit of pipe to communicate between them. And so then we'll have a master and a slave from our parent and our child. And so we can see how you would put together some kind of multi-process thing here. Okay. So as far as how these processes work, let me go ahead and connect to a software here so I can put this in the class examples area. Currently my typing is off there. That happens. For some reason in Linux yesterday, I just could not type to save my life. And that's a bad class for that to happen in. Okay, so observe zombie. Okay. We'll need that.
Zombie.h.
We'll probably need stdlib. Probably need unit std. I don't know exactly. Usually I do those later. Okay. Yeah, zombie. Okay, what I do is observe zombie. Okay, so a zombie, here's the life cycle of a process. So the process is created with fork. Okay, so after it's been created, now it's a young process just starting out, and it'll get scheduled next for execution.
Well, that's a short life cycle. It's
Yeah,
executed
it's
right
just-
after it's born.
Okay, so it'll be scheduled for execution, and eventually it will run. And it might be interrupted and it have to get rescheduled at some point, but that's what it does. And so then eventually it completes. And when it completes, we usually say at the end of it like return 0 or something, or maybe return something other than 0, but return some kind of status. And so it completes with some kind of status. And then the status, it's got to get picked up by something. It's returning something. Well, it returns it to its parent. And so that's where that goes. So the status is held around. And so the status has to be collected later. Okay, so this period between when the status is collected by the parent process and when it completes is the time when this process is a zombie. So we want to observe a process in that state. And see, normally when you have some kind of process, if we go and start something like cat, cat is running. And if we go over here and say PSAXU, this is all the process on the system. Grep for me, grep for cat. You can see I've got this process here, 40015, that is cat. And so it's got its entry into the table. If I switch back over to this other window and hit Control-C and stop it, go over here and look at this again, you can see it's gone. So it finished, and its status was collected immediately. There was never any point where it was a zombie. And you got the status over here. If you look at man PS and you look for status, status not there. Let's look at top. Hopefully one of these will have the tables of statuses. Status is like the real-time version of PS, basically. Okay, so you can see the statuses you can have. It can be an uninterruptible sleep, where it's asleep and we can't interrupt that. It can be running, it can be sleeping, it can be traced or stopped. This is usually a debugger-based status. And finally, it can be a zombie. And so you can see zombie is really an official term. It's there in the manual. It's not something I'm making up to make this sound more interesting. It's something somebody else made up to make it sound more interesting. Okay, so in order to observe the status, we have to create a process, and then the process has to end without this status being collected in order to hold it right here. Okay, making a child process is easy. We just do for. And we'll get some process ID out of that. And I think that can be stored in an integer. It'll help by going to insert mode. So I'll just go ahead and fork there. Okay, that means we're the parent. Okay, in this case, we're the child. Okay. Okay, so we can create another process as easy as that. Now, if we are the parent, the child is busy running, let's just go ahead and wait forever. Okay, we'll just go ahead and sleep. And for the child, we want to finish. Okay. So, child's going to be done for after that. Child will return a 0. And the parent is still going to be around because the parent is going to be busy sleeping.
Question.
Yeah.
So, what is the fork function forks the current process and starts another one that's the same as this process?
Yeah. And so then this return, well, that's the wrong one. That's an awk extension model. This is the right one. Yeah, so it makes this fork, and then it returns a process, a PID type. So I probably should use PID type instead of integer, but it is a number. And it'll work okay as an integer. It might throw a warning. And so what it returns, if it's the parent process, when it does this, is the PID of the child. So we get the PID of the child right there. And if we're going this way on a child, we get a 0 back from this thing. And, whoa. Yep. Serious?
Yep.
What happened?
It fell off. Well, the nut.
Like the bowl or like
The nut.
the nut?
The nut.
Dude.
And I lost the nut.
Yeah.
So, yeah.
You sure it wasn't a bolt?
The bolt's on the back. The nut's what holds the pedal on.
Okay.
That's nuts.
Yeah, I always seen a
Literally.
Yeah, that was the joke.
Yep.
Yeah.
So, yeah.
Huh. Well, I see.
Yeah.
Your pedal bearings feel nice though.
Yeah. They're good pedals. It's just the bolt and the nut was a bitch.
Yeah.
So they didn't want to stay together.
A friend of mine hurt himself pretty bad when one of those things fell off. He fell off the bike and ended up in the hospital with like.
I was expecting it.
Yeah.
Because I felt it being loose. I knew it was loose. I didn't realize it was going to fall off today.
Oh yeah, yeah, yeah. I probably should have tightened that like yesterday.
Probably, but I was hoping the long tight I was on there would hold it a little longer.
Yeah, yeah. Well, too bad you don't have it. I have a wrencher on.
Nope. I don't even have the nut, so.
Yeah, I know. If you
I'm
had
not
the nut,
sure
you
where
could-
it fell off.
Okay.
Because I was trying to not pedal.
Oh, okay. Yeah, well, that makes sense. Yeah, glad you made it. Okay, so we were talking about fork, and so fork returns a process ID or a 0. So actually, a child never knows who his parent is, because it gets back a 0 from the PID here. It mentions over here, the child has its own unique process ID, and it doesn't match the ID of any existing process group, so you get a new one, and doesn't inherit its parent's memory blocks, which is maybe unusual, which is why they put it here. And so it mentions at some point return value. So yeah, PID of the child is returned to the parent, 0 is returned to the child. So this is kind of like, if you're born and your birth certificate says your name on it, and for your parents it says 0. And, so don't think of this so much in terms of a human parent-child relationship. This is more like a turtle. Because remember what a turtle does is it buries its eggs on the sand, and then they hatch, and all the turtles make their way to the shore. And when they do it, the birds come and feast on the baby turtles, which aren't protected by any parent turtles or anything. It's not like the parent turtle walks over the children to protect them or anything. So it's more like that. Except that in this case, the parent is supposed to collect the stats. Okay.
Did you know they have like turtle protection groups where people like actually gather together and protect turtles as they hatch? Like it's a thing.
I'm quite unsurprised by that.
Like they fend off the birds.
Yeah, save the turtles. I can imagine my daughter going and volunteering to save turtles.
I'd save turtles. Turtles are adorable.
Yeah. Well, my son would collect statistics on how many got eaten.
Gotta love the disparity.
Yeah. I mean, I know which one I want taking care of me in my old age. So yeah, we get the fork and it makes the two processes, and we got those things. Okay, so the parent is just going to sleep forever.
I heard that the turtles are not actually supposed to pick them up by their shell, because that's actually part of their scales or something.
Yeah, they're like really
All right.
sensitive about their shell.
So they have a head that comes out. It can't be the skull, because the head like pops out separately with the neck and things.
No, but it's like part of their like skeletal system.
Oh yeah.
Yeah.
Yeah, it is. Yeah. Oh yeah. Oh, you said skeleton. I thought you said skull, and I was going to be like, you could totally build a turtle guillotine. Sorry, I'm more like my son and my daughter.
Turtle guillotine.
I did see a picture on the internet of somebody tossing a turtle, well, what they thought was a turtle, back into the water, but somebody commented and said something like, "That's a tortoise, they can't swim."
Okay, so when I look for A.out here, you can see we've actually got two processes called that. I meant to hit this one. So I ran this A.out. We print out the child's, only comment. And so then over here, you can see we've got our process there, A.out, which is sleeping. And so that's the parent. Parent's asleep. And while the parent is asleep, the child has died and become a zombie. And since the parent's asleep, the parent's not doing anything about it. Okay. So now this zombie just remains an entry in our process table. You can see it has a process ID number here. This is process 40163. And it's taking up space in our process table, but it's not running. It won't be scheduled for execution ever. And so it's waiting for somebody for the stats to be collected. Okay. If we go over here and hit Control-C and stop the parent and then run this again, you can see that they're both gone. And this is because the shell cleaned up the mess. We said to kill the parent doesn't handle SIGINT. If the parent did handle SIGINT, incidentally, they would still be running, and the child would still be running too, but they don't. So now that the parent has died, and a parent had this zombie child, the shell just comes through and cleans up the whole thing, obliterate from orbit kind of deal. Okay, so that's good of it. Okay, so let's have the parent actually do their job. So the parent's going to sleep. Instead of sleeping forever, we will just go ahead and sleep for, say, I think this is 10 seconds. Man 2 sleep, man 3 sleep. If I do man 1 sleep, it's like, or just man sleep, it's the wrong one. Yeah, unsigned integer seconds. Incidentally, I didn't know this, and I remember I was doing this program and trying to adjust a floating point number there, and it wasn't acting any different. It was like, what in the world? Anyway, unsigned in seconds. Okay, so I can sleep for, say, 10 seconds. That'll be long enough. And then we got to get rid of the child, the zombie. So the way you get rid of zombies is you wait on them. And so waiting on them gets rid of them. It's a funny world, you know. It's like I don't know, whatever. So wait here, it takes an int pointer to a status, and it returns a PID type. And there's a couple different formulations of it. The basic wait up top will wait on any child that has died. And so if you want to just generically, as a parent, be like, well, I want to see if any of my children, I want to take care of the first child that's turned into a zombie and get the status back, you just call wait, and it'll pick the first one it finds. Wait PID lets you wait on a specific one. So if there's only one child where you're interested in waiting until they finish and collecting the remains, you can do that and ignore any of the other ones that might happen to die in the meantime and turn into zombies. So that's the plan there. The reason it's called wait is it says up there, wait for process to change state. And in fact, it will do that. So if you wanted to start a sub-process and then in your code, you just want to like stop until this process finishes, wait for it to finish, you call the wait function. And so in a shell, for example, it would make a lot of sense to say, well, we're just going to go ahead and wait until this process is done, and then we'll go ahead and move on. Okay, so we'll go ahead and wait. And yeah, it mentions wait for state changes. Child, okay, here's the whole thing about cleaning up the zombie. So if the wait is not performed, then the terminated child remains in a zombie state. So you know it's below. And when a child has already changed states, these calls return immediately. There's nothing to wait for. So this is kind of like, when your kid says, well, I need to go to the bathroom, and you drop them off at the restroom, and then you go do something else, and you come back in 3 days. You don't have to wait for them to finish. They've already finished. You just collect them and off you go. So that's wait. So we just need to wait. Not a big deal. Okay, so these parameters up here. In star status, this gives back our status. The PID type that it returns is the process ID that we waited on, and that actually finished here. And so, for example, if we were driving along and we stopped and we let out our 4 children to all use the bathroom, then this one will tell us which one actually came out and got put back into the van. Well, except they're zombies. Oh, whatever. Okay.
Should we actually kill them because they're zombies?
There's no chainsaw method in the kernel.
Yeah. So we call wait right here. We have to give it a status. We got this int PID here. Let's change this to do a PID type. And just cause. Okay, so we're going to get back this one. Let's go ahead and print out some stuff.
So a child can spawn a child process then?
Yeah, I can. Yeah.
But if it's running through the same process as the parent one, then when it does PID PID underscore T, PID equals 4, but it...
Well, the parent of that process
Oh, it
would
has to
just
call
be the
4
child.
twice.
Yeah.
Oh, okay, that makes sense.
Yeah.
And then that child has to call 4 twice.
Well, you could do that.
Yeah, if you want to have more and more children.
Yeah.
Oh, that makes sense.
Okay, so we'll go ahead and record what we waited on here. Okay, so I'm going to just put that in here. PIDT waited on. Okay. Okay, so we waited on something here, and oh no, excuse me. That goes there. What goes in here is the status. Okay, so we'll go ahead and put that in here. That's an end. Okay, so now we'll go ahead and print out what we found. Okay, so this will give us back what exactly came back from wait. And so it should just be the the child's status and things. Go ahead and return something memorable. 42. Okay, so now we'll be able to see what value came back from the child, and so we should get weighted on whatever the child is, first status, whatever it is. Okay. So if I go ahead and build that, we'll go ahead, I've got to be ready over here. Oh yeah, good. Okay, so you can see we got a process running here, 4287. The child there is already defunct, it's 4288. If you look over here, you can see, oh, there we finished. So in the parent, we waited on 4288. That was our child, we know that. That was what the PID was up here. And, status 10752. Hey, what's that all about? Okay.
That doesn't sound good.
No, it doesn't sound good at all. So here's what happens. Maybe I should let me show you one more level of depth here, and then that'll hopefully clarify it. Okay, so you said status percent sign D, and we got that. Let's look at that status again. So percent sign C is a character. We don't really want a character though. We want more like a that's just a number. I'll put 4 numbers there, and so I'll say status as 4 is that. And then I want to break this 32-bit number apart, because status is an integer there. Integers are 32 bits. I want to take this 8 bits at a time. And so one way to do it, let's do percent sign D as a number, and then do a percent sign X as hex. So we'll see it as in decimal first, and then we'll see it in hex. And down here, I wanted to break this together and break this apart into numbers. So I need like each set of bits. So like status and 0x 1, 2, 3. No, we want the other way. 1, 2, 3, 4. So that should give me the lowest 8 bits, because I've zeroed out all of the rest of them. And so that's easy for that one. The next one will have to be 0x 1, 2, 3, 4. But now that all has to be scooched over a bit. And one way to do that is just to divide by 256. Because that'll bring everything back over. We could have also done a bit shift, that would have been fine too. Yeah, this, and 0x 1, 2, 3, 4, divided by 256 times 256, which is, I should probably be using that 2 to whatever notation here to make it clear. And finally the last one. 1, 2, 3, 4, divided by 256, raised to the third. Can I do that? Do I have to
You
do
can't
power?
No, it's
Yeah,
Howard.
you're right.
You have to just multiply it for 2.
Or you
Well,
can
it's
just
important in the
POW.
math library.
Yeah.
Or just bit shift it like a normal person.
That'll work too.
Okay, and finally, I think I want to have these status is signed, I think. That should be fine. Okay, let's see what comes out of this mess. Okay, so we're waiting on 4299. If we look over here, we can see 4299 is finished. If we look over here, in just a moment it'll finish. And yeah, that's pretty good. Okay, so looking at this stuff that came back, here's our statuses for things. 0, hey, familiar, 42, 0, 0. And we almost kind of did this backwards in a way, I was just realizing, because this is like the lowest 8 bits. And so that's the 0 to 255 part, and there's the next 8 bits, there's the next one, there's the next one. And if we look at the hex number over there, we got 2A. And if we look at 2A in hex, that would be 2 16s plus A, which is 10, right? Equals 42. So that's where our 42 is coming in here. So this reveals a lot about the status. Basically, the status treats each of these 8-bit sequences as something different. And all of them were 0 except for a return value, which was 42. There's none on that.
Why is the integer version so weird? Is that just like all the bits put together?
Well, so what the integer version is, well, looking at that zeros, the 2800, the 28, well, the places on that, you got the 1s, 16s, 256s, and whatever another 16 here is, like 256 times 16s.
Right.
And so looking at how many are in each of these places, there's 10 of these and there's 2 of these.
Oh, okay.
And there's 0 of these, 0 of these.
Yeah.
And so that apparently equals, yeah.
Okay.
9752. Yeah, so basically you can't just go ahead and take this like an integer and be fine. Okay. And it does in fact tell us at some point how the status works. And not only that, there are macros to do everything we wanted to do. So like Wexit status up there returns the exit status of the child. This consists of, whatever. Least significant 8 bits, the status argument of the child. Yeah, okay. So it gets us the right bits, basically. I'm not quite seeing how that lines up with what we just observed, because I thought we saw the second least significant 8 bits. Yeah, okay. So, status on Wexit status. Let's go ahead and just use that thing. Why not? Okay. Think about that one. Observe zombie. Okay, so finally, Wexit status. Should assign D as the number. Okay. See if we got the right thing out of that. Okay, GCC that. Okay, and in 10 seconds we'll have our answer. Okay, I thought there was a separate man page about these things that actually explained it in more detail, but I can't remember where it is at this moment. And I didn't put it in my notes, so sorry.
Wexit.
Yeah. Okay, so there's a number of macros here that take care of this stuff. I kind of like how they have Wexit. Oh yeah, Wexit status gives us 42. So it picks out the right bits. I still don't, I'm still puzzling over why it's not here given what the man page said. I expected it to be here because I've done this demonstration before and it's here. Okay, here's an error in the manual. It could be. They exist. Okay.
Update the manual page and become famous.
Yeah, exactly. There's somebody in my Linux class that wrote a manual page, just like for fun.
For what? Their program?
Yeah.
Huh.
Yeah, like I assigned everybody to write this little script. Oh, but he was writing a different script for fun. Like he wrote a program for fun, and he was using the argparse library in Python, so it looked all professional. And he wanted to have a manual page, so he wrote a manual page in man.
Oh, that's cool.
Yeah, it is. I feel like I should assign people to do that now in the future.
I should do that with my keylogger.
Yeah. Well, what are the chances they're going to say like man keylogger?
Man, this is definitely not spyware.
You guys are supposed to name it something that people won't actually guess.
Well, it says it's not spyware.
Okay, well,
like-
that's good.
Yeah. It provides an automated backup of passwords.
Yeah, exactly. with the Python script, get passwords now.
Right.
.py.
Okay. So I got it.
Pie.
Yeah. So I got a pretty good observation of zombies. Kind of explains the process status and how all that stuff works. I'm going to just leave this one in this form. But I want to go ahead and make a setup where we have use the child process to accomplish some purpose. Okay, use children. Let's see.
That doesn't sound good.
Yes.
You guys figure mine out.
Wow, I was never in the crowd.
Sounds like something they talk about in my class I'll have later today.
Oh, you
You're using children? What class is that?
Oh, it's an interdisciplinary.
Oh.
Okay. So we're going to have some PID here. And we actually might want multiple children if we're going to get a lot of use out of them. We'll switch it later. Okay.
Sweatshop.c.
Yeah. Okay, so we're the parent. I always find it a little confusing there when you write it this way, because it's the child's process ID, so it makes a lot of sense to name the variable after the child. But then we say, if child, we're the parent. So I usually put a comment there. Okay, so if we're the parent, we want to be able to assign this child to go do some kind of work for us. And so what we want to do over here in the child is like read a job, do the job, return the result without dying. Okay. So in order to do this, we'll use pipes. And so what the parent has to do is send a job. Okay. So that's the parent algorithm in a nutshell. So what we need to do is we do some pipes. And if we look at the man page for pipes, we can see we've got this function pipe, and it takes an integer array, which is file descriptors for the pipe, and it'll return us an integer that basically says whether or not it worked. If we look at the return status, return value down here, on success, 0 is returned, on error, -1 is returned, and error no is set appropriately, so we can see what went wrong with the pipe. So it's a good idea to check the return value in this stuff. I can't necessarily guarantee you will bother. And it's got this integer array that's going to get changed there, pipe file descriptors. So we got to make our pipe ahead of time. So pipe, and so we need some file descriptors, pipe FDs, and there are 2 of them. Okay. Okay, so this makes us a pipe. And so at this point, it's possible to read into the pipe and get stuff back out of the pipe. So here for a child, we should be able to read some kind of job from there. So we want to read from the pipe file descriptor. Oh, we need the right end of it. I think it's going to be the second one. If we look at this, it mentions it creates a pipe. It's a unidirectional, one direction, data channel that can be used for interpreting process communication. Okay, so it returns 2 file descriptors referring to the end of the pipes. Pipe FD0 refers to the read end of the pipe. So I actually got it exactly backwards. And pipe FD1 refers to the right end. Okay. And here's a funny thing. Oh, well, that's not a funny thing. Data written to the right end is buffered by the kernel until it's read from the read end. Okay. Mentions for further details, we can see pipe in manual section 7. And it's just an overview of how the pipes and first in, first out queues work. So basically, this is like my lecture outline for today. And so we'll go ahead and use the system, and I'll show you how it works. And then there we go. Okay. So we want to read from file descriptor 0. And if we look at read. So read, we got to get a file descriptor here. We also need some sort of buffer to read into, so we got to make that. And then count here is the size of the buffer, like how much we can read at once. And so then after that, we'll get a size t that indicates how much we read. And it is a size t. So the return value on read here, on success, it returns the number of bytes that were returned. 0 indicates end of file, which means that the right end of our pipe got closed and there's nothing more left in it. And then the file's position's advanced. Okay. And so then it's possible that we have an error, and in that case, -1 is returned. Okay. So let's go back to this use children. We'll read from a pipe, and we need some kind of buffer. So I'll go ahead and make one. Charge data, say it's 1024. Okay. And we should probably keep how much is read. start off with 0 at the beginning. Although it doesn't really matter because it's going to be set right here.
What is an SS size T?
It's a signed size T,
Okay.
which is a weird concept here because memory addresses on this architecture are 64 bits and they're unsigned. And so here we have a type for those that's signed, and it only provides 63 bits worth of unsigned addressing instead of 64. The reason is that way an error code can be returned. And 64 bits, if we do like, okay, so 2 raised to the 32, so there's 4 gigabytes for you. And so this is, 4 gigabytes is not that big for memory size anymore. My laptop has 2 gigabytes and it runs out of memory all the time. But what we need is, about this number here. I mean, that's like one longer. That's 18 gigabytes. We don't really have, even that's possible. This would be 184 gigabytes. This is an uncommon amount of main memory to have. I software cut 128. And I think I could have spec'd 256 if I had an extra couple grand for it. Might have been like $3 actually. Anyway, it was more expensive back when the software was made, and it has error correcting memory because it's got so much of it that errors are a distinct possibility. But that's about as much as we can use. And so we've got a lot more space available here in terms of, each place here is an order of magnitude. With a signed size T, we're cutting it down to this. But again, we're only about this many places out, So it's plenty big enough. Now, in a way, this is terrible. This is like an engineered limitation where the way the function calls are defined limits what the architecture is capable of, at least with that operating system. But it's not a problem yet. This is a problem that you might have to solve like mid-career point when we got, the exabytes of main memory.
I wish.
Yeah.
At what point do you need error correcting memory? Like 32 or 64?
Well, you never need it. The thing is, the error rate goes up the more memory you have.
Right.
And so at some point, having the error correcting codes, even though they slow the memory down, actually helps you because you don't have to account for so many errors later. Like the errors can be, they'll eventually manifest somewhere. Somewhere more expensive. The usual, well, okay, it's kind of changed over the years, but the usual kind of floating standard is that if you've got more on your machine than is supported by desktop hardware, then you probably need error correcting memory.
Okay.
And so right now, an LGA 2011 system, like desktop system, you can have 64 gigs of memory. And so if you have more than that, you probably want error correcting.
Okay.
And I realize that's just like a floating, nebulous, meaningless standard, but it tends to mostly work because the memory has been getting more, improving at about the right rate to make that so. Yeah. Okay, so your data, and this is the size of the data, which is 124. Magic number, I know, whatever. Okay, so Reed is going to go ahead and throw all this stuff through. And here's an interesting thing about the pipe. So the pipe buffers this stuff in the kernel, right? And so if you say, well, this is an excellent mechanism. I would like to encode my entire DVD collection in Ogg-Vorbis format instead of MPEG-4. And so what I'm going to do is I'm going to set up a program that runs the encoder, and it's going to have a pipe from another program that takes all the files and runs them into this pipe. So I'll just go ahead and stuff our DVD collection into the pipe. There is an upper limit to what you can put into a pipe. Because it does have to allocate memory in the kernel for this stuff. And so it doesn't even have a good way to page this stuff out, It's like when you fill up main memory, that's like it. Okay, so the pipe mechanism is good for transferring small amounts of data or a data stream where it's going to be consumed more or less as it's written. Because you can blast as much stuff through the pipe as you want to. It's fast that way. You just can't stuff it full. I mean, this is a pipe, not a reservoir. Okay, so we're going to read from this pipe, and then we want to carry out the instruction. And so we'll have some instructions for this child, I guess. I don't know what kind of format this is going to have. I guess I need to make some kind of protocol here to control the channel, don't I? Okay. S is sleep, or 1 second. Okay. And maybe I want to have something where it calculates something. That would be good. F, calculate fib.
So is this pipe thing in here just like the stuff used, like if I pipe something into grep or something, does it kind of use like that?
Yeah, it does. But this is the direct interface with the pipes. When you put a pipe on a terminal, the shell organizes things so that standard input and standard output are run together to run everything into your program. And it's going to involve the pipe interface, but the shell is setting everything up for you. So we're at the level of what the primitives that the shell uses right here. But yes, that's how it's done. Okay, if data 0 equals ANS, we want to sleep. I guess I only need like one character here. Okay. F, and then we want to calculate the 40th Fibonacci number. I did that because it'll put a load on the system. So if I cat C, there's my Fibonacci thing that I keep using all the time. We'll put that into use children. Okay, so that should have appeared right down here, and indeed it did. We don't need that. All we need is main. All we need is this. And so I'll have to go ahead and print that out. We can print directly from the child, that's okay. And fib 40. Okay. There we go. Now, it's possible that data len will be something else. And we got to account for that first. So if data len is less than or equal to 0, either we got an error or the pipe is done. And so we'll go ahead and die. Okay. Okay, so we got this child, 1 equals okay. Okay, we'll go ahead and return a 0, which is the usual no error, everything's fine status code. Okay, we should probably put some kind of note here about this being received. Okay, and just change this ending. Okay, so now we should be able to tell on our child if it slept. If it calculates the 40th Fibonacci number, we'll know because it'll print it out. And so we can see what's happening. So up here in the parent, we can go ahead and use this stuff. We can write into the pipe FD's at position 1. Look at writing in a minute. So write takes a file descriptor. That's what we gave it, the file descriptor for the write into the pipe. It needs a buffer, and it needs the amount of stuff that is in the buffer. And it's a const void buffer, so we can actually specify like a string there if we want to, and that should be fine. A string is a memory address. It's expecting a void star because we don't have to just write characters here. We can write any data we like. We can write an array of integers if we want to. It'll go through the pipe. The pipe is binary. It's not using ASCII. I used ASCII because ASCII is easy. But we could have written like numbers into the pipe and read out a 1 or a 2 or whatever. Okay, and the size t that comes out is how much we actually wrote. And so that'll tell us if everything's okay. Okay, so we'll write a, say, something to it. Say we want it to sleep. And the length of data we want to write is 1. And that's like it. Okay, that's how we send it in an instruction. And we'll say sleep, do the Fibonacci number, sleep, and the Fibonacci number. And then after that, we're done. Okay, go ahead and close it. Now there's one other thing that has to be done here. This pipe is unidirectional, one way. And from the parent process, we're going to write into the pipe. From the child, we're going to read from the pipe. We need to close off the extra ends, because the parent is going to have both ends of the pipe. The child's going to have both ends of the pipe. The parent doesn't need to read in. The child doesn't need to write in. It would be okay if we just ignored that issue, except that when we closed our end of the pipe, the child wouldn't read a data len of 0 or anything like that, because the child would still have the pipe open. And as long as the child's got the pipe open, it's not going to be an end of file. The child could go write stuff into the pipe on its own, and that could be a problem. Okay. So we're going to close the right end of the pipe in a child. Okay, let's see what this whole mess does. It returns error, conflicting types for fib. F undeclared because I didn't put a character symbol around it. Expected a semicolon on line 39. I guess let's start there. That's the first one. Okay. And there's a place where for F, I forgot to put little ticks around it. Not backticks, or single quotes. Right, put single quotes around it. Conflicting types for fib. Go ahead and take this away and put it up top, because I didn't bother with the function prototype, instead I'm going to do that. Hey, there, cool. Okay, child is beginning sleep, child is ending sleep. So now the child's probably calculating the Fibonacci number. Maybe it's done. Maybe it's not done. I was expecting to see some use there.
Well, maybe the child struggles with math.
Did the child die on us? I think the child died on us. Here's the problem. Here's what happened. So the parent died almost right away, because we went and wrote this into the pipe, then this, then this, then this. And we never waited for the child to finish. And so probably what we've actually done here is we wrote into the pipe SFSF, and I bet the child read it all out at once. Like, we didn't get a good rhythm going here. Like, you know, write it, and then that happens, write it, and that happens, write it, and that happens. I'll go ahead and have this out with sleep.
So he got overwhelmed and then just died.
Well, not quite. What he did is, let's put one right there, and let's put it, let's hold it at this status for a while at the end. Okay, now I want to. Okay, and okay, so I'm betting what came out of that read. So we were coming through here, we're at the parent, we hit those write blocks. Each of the writes is fast. The odds that this thing will get interrupted between writes are pretty low. And so I'm guessing in the child, we hit read, and what we got back into our buffer was like SFSF, and so that's our buffer, our data.
Oh, so we got to the last one, and then after that it...
Yeah, so just looked at the first one, and then it went back up there to read again, and probably just kind of died transparently. And
Sometimes it networks all the time, but networks all the time.
yeah, and it you know, works the same. We're probably just waiting on this read and not getting anything back from it. Okay. Okay, so child's beginning sleep, ending sleep. Hey, what do we stop for? Did I miss something important? Did the child die? Didn't say it died. So when we read here, we have to print off either one or the other of these things. Let's go ahead and print off what we read. Good. Percent sign S is right. Oops. That's interesting. That's kind of not what I expected the child to read. So child read, oh, I said percent sign D, not percent sign S. That was memory address of the data, well, 32 bits of it anyway. Okay, so we read an S and some other stuff apparently. Let's go ahead and check and see what the data line is. Oh, it's probably not null terminated, is it? Of course it's not null terminated. Because we just wrote that, we wrote one character. Maybe we should have, instead of that, written like a, you know, like 2. Because that'll be the null terminator on the end of it too. That might make some difference. Okay, now we wrote an S. Okay, we still didn't do that. Did we put this in a loop? No. Okay, so today is sort of my daft day, apparently. I didn't bother to do a loop here to read this thing again. So I got to the end and finished. I don't know why while 1 it makes sense this time and 4 : made sense in all the others, but apparently it does. Okay, so there we go. Now the child should continue working until we're done with it. Better. Okay. Child read an F. Hey, there's that calculation. Good. It slept. It read that. And now the child dies. Okay. And so the parent is finished, and the parent's beginning his sleep. And so if we look over here, the child is a zombie at the moment. And so we probably should have waited. That would have made a certain amount of sense. But we didn't do that. And so eventually the parent finishes sleeping and goes away. And the shell takes care of all that stuff. Okay, so let's change this just a little bit. We sent in all of these commands here. Let's make the last command be a Fibonacci. It is, that's good. And then we won't bother with this sleep, and that'll be fine. And we won't bother with this one. We'll just go ahead and wait. So parent is finished and beginning to wait. And child has died. Okay. We'll need this actual status variable here. And so we'll just go ahead and wait. Wait returns the PID. Don't bother to collect it for now. Okay. So this should result in the parent waiting. What? And what was it? 2.
I think it was just
Oh.
Wexit.
Was it just Wexit?
I think so.
I see Wexit status here though. Maybe I forgot to include something in there. Did I do stdlib? No.
Who wrote that? Elmer Fudd? I mean Wexit?
That's wait, exit status.
Yeah.
Like when it comes back from, yeah.
From the web account for status.
Okay, so you see how we stopped a moment, and then as soon as the child finishes, the parent is done. And so if we want to, we could change this a little bit, like say on a child, say we decided to give the child something that actually takes more time to do. We'll say the Fibonacci number of 43. And we probably don't want to send it this extra F right there, because 43 is going to take a little bit longer to run. And so at this point, it should be that we actually wait a moment. Okay, see, we're waiting for Fibonacci number 43 to be calculated. And then as soon as it's done, the child dies and reads a data len of 0. And so there it goes. And then in the parent, we wait on the child. So we can wait for it to finish. Okay, now suppose we want to actually do more than one child. No problem, we can do that. What we have to do up here is, first of all, we're going to need a pipe to communicate with each of the children if we have a bunch of them. And secondly, if we want to have a bunch of children, we're going to have to fork and produce more than one child. And so we're going to need some kind of array of children. Okay. So I'll have some kind of array of, say, I don't know, C num. That's the number of children. And, say 24. Okay, so I'll have 24 children here. And so we have this, this array of children. We won't do that quite that way. We're going to have a lot of these children, and each time we loop, we're going to either have to continue or not. Like we need some kind of loop that creates children here. And so in order to do that, we have to check and see if we're the child. And so if we're the parent, we might need to go back and make another child. Meanwhile, all the children are going to go down here and start reading from this, these pipes. Okay, so somehow the children are going to have to know what number they are. And so I'm going to say something like child num equals 0. Let's start on child number 0. Okay, so there's this child num is going to be available down here. And so the pipe that we want to read from is going to be our, well, we need to array these things first. So a pipe file descriptors is like 2 of these things. And so we want an array of those things. If I remember right, in C, we just put it right here. Like we want an array of these for a 2D array. Is that right?
That's
It'll
right.
might not work, but, yeah.
It might not work, okay.
No,
You say it's right.
that'll
Okay.
work.
Okay, good. So that's all our pipe file descriptors. This is going to be part of making a child. And so we're going to have to keep this around in some form. But down here, we got all pipe file descriptors. If we're the child, go ahead and make this, we're going to read from all pipe file descriptors, our number. Did I call it C num? Current child num? I don't remember, child num, as I call it. Okay, so this at child num, and I feel like I may have opened a parenthesis here or something. There we go. Okay, now we're going to have to close all pipe file descriptors. Okay, now this child num. Remember that all the variables are duplicated when we hit a fork here. And so as the child, we're going to get child num. Like that's available to us. And as the parent, we're going to go change it, and that's fine. It won't change for the child. They're not shared. So that'll be fine. Okay, so we got a child number that we're on. So the process of creating a child. What we have to do is, first of all, make our pipe. All pipe FDS set position, child num, like the one we're currently on. And so then after that, we got a fork. And then, if we're the child, we have to, well, first of all, close file descriptor 0. That was the read in. And then we have to increment child num. And then we have to go make another. Okay. So all this stuff can be done. We're going to have to do our little if child thing here for if we're the child.
Yeah, so I don't think programming language development has advanced that far yet. Make another.
Yeah, okay. So now this part down here, that just goes in. Okay, so if we're the child, we want to close file descriptor 0 there. We want to increase our child num, and we want to go make another. Well, luckily, our programming language is very advanced.
Really?
So then we'll go make another. Oh, if is less than the number that we want. C num. Then we'll go make another. Okay.
You get schooled on that one, Kyle.
Wow, I'm surprised.
His mind is blown.
Okay, so there's the little child maker process, and so all the children are going to follow through there to the lower one, and
Embarrassed.
and so then down here they are busy waiting for stuff to happen. Okay, so if we hit make another, we're back up there. Assuming we didn't, then we're down here. But we need to send some jobs to children. Okay, so we'll go ahead and make them all calculate the Fibonacci number. I'm going to give them something higher, so it takes a long time. And so this is the single child version, reserved. Okay. And so that's going to be down to there. Okay, so we got to write the multi-child version. And I really just want to make them all go do something that takes a long time. So, for anything to say there, child num greater than 0. Actually, greater than or equal to 0. Well, greater than 0 is fine. Child num. Let's go down our children until we get to the bottom. Okay, so then I want to write into pipe FDs at position 1. So, excuse me, all pipe FDs. The thing we want to write, Fibonacci, and we want to write 2 characters, so we get the null terminator at the end. And then after that, we can just go ahead and close our end of the pipe. Okay. So once we've dumped our end of the pipe, then the child, it's going to hit this, calculate the Fibonacci number. And then after that, it's going to find that the pipe's ended, so it should die just after calculating the Fibonacci number. Okay, I want this to take a little longer so it's more easily observable. And so I'm going to go ahead and do Fibonacci number, say 48. That should take a moment. Child instructions don't have to change. Okay, let's see what this does.
What's the biggest one you've done with that program?
I don't know, probably not 48. Pipe FDs. Oh yeah, we replaced that. Okay. Child equals fork, child undeclared. Oh, yeah, good point. Okay. Okay, so a bunch of child's read F. Oh, I should have stuck around. Hey, they're all running now. So all the children are busy happily calculating their Fibonacci numbers. The parent is dead. They don't know it. It doesn't seem to be bothering them very much.
So they're orphans?
Yeah, they're all orphans. They get adopted by ANET.
The orphans of the war.
Yeah.
What?
What? Because their parents are all dead, but the child doesn't know, so.
Yeah, they're all running. But yeah, when you have one that's like this, where there's no parent, it'll get adopted by the init process, and so init will actually be their official parent. Oh, they're starting to die out because the CPU usage is going down. A few of them took longer for no particular reason that I see. And so you can see we're starting to get, oh, look at that. We had a data type problem with my Fibonacci thing. Didn't know that. My point was to load the system down with all kinds of children that were doing stuff, and we did that.
Oh, well, that makes sense, though. Because it would have wrapped around
Yeah. I didn't realize FIB 48 was that big. We could change from an unsigned int to a size T. Is that going to be okay? Yeah, X can still be an integer. Yes, that's fine. And then down here, when we print it, we have a long number. Not tail end, right here. Oh, and I wanted to make the parent actually wait for all the children too. So after that, for child num is less than cnum. I realize I'm running these loops in opposite directions, but I don't feel like declaring a variable like outside the loop. And I don't feel like passing it the std equals c99 flag. And so this avoids both of them by just running it whichever direction child num has to go. Anyway.
So you don't want them to be orphans?
Well, no, I don't.
Okay.
Okay, so we're going to go status. Okay. I'll go ahead and preserve what we waited on here. Sort of thing makes it readable. Pseudo space. Sometimes you gotta start calling me underscore. This is pseudo space. Okay. Okay. Okay, that would be waited on, and then the status. Well, exit status, and how many are left? Child num. Okay. Oh no, that's how many we've waited on. There we go. Okay, done waiting. Okay, waiting on children. Okay, so you can see the parent is still in fact around. And if we go over here, we can see a software is loaded down with 24 processes.
That's a lot of kids.
Yeah, it is.
They could get their own TV show.
Yeah,
You can
real
make
kids
a
are harder to bulk
soccer
manage than this. And they do a good job in daycare, but there's always like one of them needs something special.
48 kids and counting.
The one that's the slowest in calculating Fibonacci.
Here's the other thing that's interesting on this. It looks like our CPU temperatures have gone up and we're touching the 60s. It idles in like the 40s. And it sounds like a vacuum cleaner.
Yeah, 60 degrees is about
I think we did
100.
see Asoptra last semester in networking, right? We went down to the data center and looked at Asoptra.
Yep.
Yeah.
Yeah, I saw it. You can see his cores are still busy working on something. See, most of them cool off. There's one of them that's sticking to 57 up there. If we look at this, there's just like a few left. So there's probably another hot core up here. Yeah, 59. And
It's about
well, it's primary.
it's about 130 Fahrenheit-ish,
Yeah, something like that.
something like that.
Oh, looks like they're all done. All the processors are cooling off.
Where's the number? Oh, that's on the other terminal.
Oh yeah, that's in the well, not that one either.
Yeah, it's in Celsius.
There, that one. Or not that one. Numbers would be up here. I like that worked.
That should be on the final. What's the 48th Fibonacci number?
Yeah.
That's a terrible idea, Gus. Let's not do that.
You don't want to calculate that, Kyle?
Huh?
You don't want to calculate that?
No, I don't. Why would I want to calculate that? Why
Well,
would anybody want to calculate
I can just put on the review guide that you need to memorize all the Fibonacci numbers up to the 48th. And then just ask for one of them, multiple choice style. In fact, I could make it easy. I could have the multiple choice, have like, I could be like, okay, what is the 48th Fibonacci number? Then have a multiple choice where you have like the, 46th, 47th, 48th, 49th, 50th.
God, isn't that what I sound like when I suggest really hard problems for the final? Because that sounds really annoying, actually. Sorry, guys. I finally gained some self-awareness.
Yeah, probably.
See, you're just an Elmo, Kyle.
Scratch my head.
Okay, so that's the whole waiting on children and zombies and setting up a multi-process thing. So you could totally use this method if you had some kind of bulk data processing you needed to do, and you were running on a machine with a whole bunch of cores, and you want to spawn a bunch of processes and do it. And in fact, with the processes, instead of lightweight threads, remember a lightweight thread runs in its parent's memory space and it doesn't require a second entry in a process table. You get that with pthreads or other things like that. With this, you got a whole process, and so it's a little bit more work to create it, but it's kind of independent once it's done. You just got to maintain that pipe. So there's a cluster operating system out there. It's Linux derived. It's called OpenMozix. I've actually hacked on the code of it before to put in support for hyper-threading awareness. And what it does is you set up a bunch of computers, you run OpenMozix on them, and then when you spawn off a process, it can be scheduled on any of the machines in the cluster. And in that case, the pipe goes across the network. But if you're in 435, you probably remember the network socket looks an awful lot like a pipe with the whole read and write coming out of it. And so it's very easy to map the pipe into running through a network socket and then pull everything out the other end. So then you have these processes, and they get scheduled on whatever machine they get scheduled on. And so then you just say at your on your one of the nodes, okay, I'm going to run this process. I'm going to make like 50 child processes. They all get farmed out. They all get done in parallel, and you get your results back. It was a good idea. It has some practical inefficiencies because you don't have any concept in the scheduling of this process is going to end up on my node. And so when you're designing your program, it's hard to know what the actual overhead of your pipe is. And a pipe inside a computer is extremely reliable. A pipe over a network has a lower reliability associated with it. And then finally, suppose that you have some bulk data processing. And say you have a bunch of image data, and you have 6 gigabytes of image data. And so what you're going to do is load all your 6 gigabytes into main memory, then you're going to hit fork, and then you're going to carefully have your processes not modify that 6 gigabytes, but instead they're computing something based on it, so that it doesn't get duplicated. It could be more than 6 gigabytes. Suppose you're loading this on a software and it's 120 gigabytes. In that case, you'll be fine, normally, because when you duplicate a process with fork, it doesn't duplicate memory unless you start writing to it. So your 120 gigabytes of image data is perfectly fine. All of your children can read from it and do whatever they like with it without causing duplication. Well, if you introduce to OpenMozix, now that whole 120 gigs is going to have to get copied to the other machines in the cluster if they get one of these jobs scheduled. And that can be a problem. I mean, if you're going to design this to where 120 gigabytes copied to a machine, I mean that's 120 gigs over the network takes a while. And then you're assuming all the computers in the cluster have that, of course. And then if it gets scheduled on another one still, you're going to have some other copy. And then suppose your computation looks like this. Suppose you start off with everything in a single spot. Okay, we're all starting off unified, and now we're going to make all of these children, and all the children are going to find some data, and they're going to return it to the parent. I'm going to make the parent a different color. So the parent continues down here too, but all the children return their data to the parent. So there they go. Okay, and then the parent does some amalgamation and stuff, and then spawns the children. And they get farmed out to all their nodes again. Well, if the nodes that these got farmed out to, they had to put that 120 gigabytes in main memory across the network, and they're not going to keep this around once all the children are done that were using it. So now you have to do it again. So another model that'll support this kind of computation a lot better is one where you establish a worker process on each of the cluster nodes, and then the parent just tells the worker process on this node, okay, here's what we're going to do next. And then that process makes all the children. And that tends to work a lot better. There's another API for it. It's called MPI, Message Passing Interface. And it's designed to have you establish a process on each of the nodes you want to do, and then send messages to them from the parent, which tells them what to go ahead and do. And that can result in a lot more efficient memory usage and a lot less network usage. So it's kind of taken over. But OpenMozix was a cool idea. It was big for a little while, and then people were like, the reality is, it's not that common to have a processing task where this is really ideal. And MPI is a lot more flexible because it tends to encompass a large majority of the parallel processing jobs. The other category that OpenMPI doesn't really handle is all of my processes are absolutely, truly independent. And in that case, you might as well just go ahead and have them be independent. And that works fine too. I've used that processing model a lot. Oh, anyway, I'm over time. Any questions? Okay, cool. Well, now you know about processes and how to exploit that. So next week, I think we're going to dive back into the book to go through chapter 6. I kind of wanted to cover some of the more, I don't know, practical aspects first. And then we'll go look at the process scheduler a little bit in 6, and we'll move on. I really wanted to play with the kernel on this machine, and I should probably just set up a different one. I haven't got a chance to come and figure out what's wrong with the stupid thing.
Make Kevin do it.
Yeah, I guess. I don't know. Kevin can re-image it.
Well, yeah, you can just, this one's broken, can you re-image it?
Yeah.
Just make Kevin fix it.
And that might be the thing to do. Just have it re-imaged and then go build the kernel again. Okay, I'll see you all next time.